We would like to find the local maxes and local mins of this surface. F of xy is x squared plus y squared times e to the minus x. The first step in this problem is to take the x and y partial derivatives. So that has been done for us here. We will take more derivatives later, so we'll still get to see some derivatives in this video, don't worry. But there's a product rule for the x derivative. So there are a couple of terms that happen because of the product rule for the x derivative. There's no product rule required for the y derivative, so that is simpler. Now we have these derivatives. What the first thing we want to do with them is we want to set these equal to 0. So we set each the f and y partial derivatives equal to 0, and we want to solve. We want to see what set of points satisfies both of these equations simultaneously. Those are our critical points, the points where both f x sub x and f sub y are equal to 0 are the critical points. So at this point we can choose, do I want to work with this equation or this one? And I want to work with the second one because it's simpler. So with the second equation, if this is equal to 0, that tells me that y must be 0, because e to the negative x is never 0. So if this product is 0, it must be the y that's 0. So I know y is 0. I'm going to plug that in, plug y equals 0 into the other partial derivative. And what happens then? If y equals 0, we have e to the minus x times 2x minus x squared is 0. That's e to the minus x, e to the minus x times x, 2 minus x equals 0. And we see the solution is x equals 0 or x equals 2. We have two critical points we have found. Our critical points are, we have x equals 0 with y equals 0, and we have x equals 2 also with y equals 0. In general, in these problems, you could have any number of critical points. For this problem, we have two critical points. All right, so we have the two critical points, 0, 0, and 2, 0. I've written the first partial derivatives down again because in order to classify these critical points as maxes or mins or saddles, we need second derivatives. So we need to start with these first derivatives and find the second derivatives. Whenever there's exponentials involved, I think it's nice to factor the exponential out. It makes the next derivative easier to deal with. But let's compute f sub xx, the second partial derivative. This is again a product, so we again have the product rule. We have a negative e to the minus x times 2x minus x squared minus y squared. That's f prime g plus f g prime 2 minus 2x. So that's our second derivative. And the second derivative of y with, or the f sub y derivative, take another derivative here, is just 2 e to the minus x. That derivative is simpler. And we also, in order to use the second derivative rule, we also need the mixed derivative. We need f sub yx. And we know that's the same as f sub xy. So we can choose if we would rather start here with f sub y and then take an x derivative, or start with f sub x here and take a y derivative. It's the same either way, but this is pretty straightforward. I'm going to take the x derivative of f sub y to get minus 2y e to the minus x. So we have all of the pieces we need, and the second derivative test can be organized nicely in a table. I'm going to put the point 0, 0, and 2, 0 are our points. I'm going to put the discriminant d, which is f sub xx times f sub yy minus f sub xy squared. And we're evaluating that at our points. So I plug in here f sub xx at 0, 0 looks like 0 plus 2 e to the 0. So 0 plus 2. I'm going to put that in my table as well. I need f sub yy at 0. F sub yy at 0, comma 0 is also 2. And finally, f sub xy at 0, 0. I plug in a 0 for y and a 0 for x, I get 0. So the discriminant is the product, f sub xx times f sub yy minus 0 squared. So this is 4. All right, so when the discriminant is positive, we either have a max or a min. And if the second derivative, f sub xx, is positive, that means we have a local min. For the other point, we do the same thing. Plug in f sub x, 2, 0 into f sub xx, f sub yy, f sub xy. We get negative 4 e to the minus 4. For f sub xx, we get negative 2 e to the minus 2. When the discriminant is 0, we have a saddle. So we have a local min and we have a saddle for this particular example. On some problems, we'll have more points and we just have more classifications, and it's more evaluating of f sub xx, f sub yy, and f sub xy. But that is a good way to organize these second derivative test problems and get the right conclusion.